right, so into week 3 here. Hopefully PA2 is moving forward. All right, so want to go over the ODPs and any questions on programming assignments, etc. Hashes so far. So let's run through ODP really quickly. So 209 was deleting the middle of a linked list. So basically taking this first node and having it point to the third node. So I went ahead and used a temporary node pointer called temp, set that equal to the original node's next. Right, so here's pointer. If I set temp equal to pointer next, then temp is pointing to this node that I want to delete. So temp is the node I want to delete. And then I set my pointer next to be temp next. So pointer next is this field right down here. This is temp, so temp next is this field right here. And when I say pointer next equals temp next, it takes whatever is in this location and copies it into this spot. Since this location is pointing to the third node, when I copy it over here, pointer is now pointing to the third node. So temp has been excised from the list. So that statement basically causes the first node to skip over temp and point to the third. And then I go ahead and I say free temp. And the reason I use the temporary here is the following. So here's pointer, which I called n. There's your list. If I were to do this, pointer next equals pointer next next, that's fine. Because pointer next next is this node. If I set pointer next equal to that, I removed that middle node, but I have no way to free it now because there's nothing pointing to it. If I were to say free pointer next, what am I going to do? I'm going to end up freeing this node because that's pointer next now. And if I were to free pointer next before I do this, as soon as you free a node, think of that node as no longer existing. And so when I try to say pointer next equals pointer next next, well, pointer next was pointing to something that doesn't exist. I can't guarantee what this is going to do. So that's also the frowny face. So you kind of have to use a temporary in this case. We've got to remember what this node is that we're going to delete, or we have to remember where this node is pointing. Go ahead and release that node.
Is there a way to do without a temp?
I don't think so, except maybe something tricky like an XOR. You got a way?
Well, all I did was the middle line and that worked fine.
Just this?
Yeah, just that.
It'll assess fine, but you're not actually releasing the memory. So, which I didn't check for, so. There's undoubtedly some fancy way you can code it up in C that'll look like you're not using a temp, but it'll be using a temp underneath, I think. All right, so 210, function called edit2. So here you're starting with a list that contains only 2 nodes, and you're inserting a node. You're starting with a list that contains 3 nodes, and you're inserting in the middle. So your function is passed a pointer to the first node. And it looks like this. And you don't need to know what the data is that's inside here, but for example, I don't know. I'll just put question marks, because the data in there doesn't affect us. What you want to do is create a new node. And we're passing a number, num. So this is going to have num. And you want to change this to point to this node and have num point to that last node. And it's important when you do this that this is actually what you're doing. You're creating a new node, you're changing the second node to point to that, and changing that to point to the third. So if you were to do the following, you'll actually get 100% on the assessment, but this is not the same thing. But somebody may have done this. So you create a new node. You copy this data value into here, you write num into here, and now you just add that new node to the end of the list. The result looks the same if you traverse the list. You got that thing, new thing, and then the third thing. But you're doing something fundamentally different, right? You're not just sandwiching something in between here. You're putting something onto the end of the list, and then you're swapping, right? So you want a house between this person's house and that person's house. One way to do that is to build a house in between, which is what your customer asked for. Another way is to build a house over there and say, okay, well, you have to move into that house, right? And you pick the people up and move them over there, and now it looks like this new house is in between. Right, so that's what this is. So make sure, because that'll totally mess us up when we're dealing with trees. Or if these things are not just simple integers, if these are large complex structures with lots of levels to them, we can't just pick one up and copy it somewhere else. So just something to keep in mind. All right, so any questions on any of that? So hashes. So we went over the basic idea of a hash, right? You have a pair of data, key and data, pair of items, and we're going to store the key and the data in a set of arrays, parallel arrays. But instead of just storing in the next sequential location that's not in use, we're going to somehow transform the key into an index in a way that hopefully takes us to a spot that's not already in use. So there's this hash function. We'll just call it h, which takes a key and gives us an index. This is not a pointer dereferencing. In fact, we're probably not going to deal with pointers in this part of the course. So I'm just saying that this function returns an index. And then you use that to access your array.
You normally use an array for hashes, or?
Yeah, usually an array, because they're really quick to access once you have an index. Okay, and then there was this question of collisions. So collisions happen if you have 2 different keys and they hash to the same index. You can't store 2 things in the same location. So we need to find a different location for that second thing. And we might just go on to the next location in the array. And if that's in use, we'll go on to the location after that. And that gets us into this problem of clustering, where we have a bunch of entries stored in one spot. So instead, we can have a modified hash function, which actually takes two arguments. So the first argument is the key, the thing that you're trying to hash. The second one I'm going to call a probe. And the probe is kind of like the attempt number. So here's what we're going to do. You've got a new key, and you want to store this key and the data in your hash. We're going to call our hash function with a probe of 0. And we're going to take whatever value this gives us back, and we're going to say, can we store our data at that location in the array? If we can, great, we're done. If we get a collision, if something's already at that index, we're going to rehash with a probe of 1.
Would you normally do that check within the hash function and recursively call it? Or
No,
outside?
I would do it outside. So index equals so the hash function should just take a key and a probe and give us back an integer. So set that into some location. Can we store it at that index? If not, then recall your hash function, but use a probe value of 1. And if that location is also occupied, rehash with a probe of 2, and so on. So that's just a for loop or a while loop. Right? Set your probe equal, we'll put some code since it's Friday. Probe equals 0. Index is whatever we get back from the hash function. And we've got some magic function we wrote called collision, which tells us if that index gives us a collision. So if we get a collision, bump up the probe and rehash. Or whatever your favorite loop structure is. So the punchline is, when we hash our key, we keep trying. If it gives us a location we can't use, we rehash with a higher probe number. And hopefully, eventually, we get to some probe number where this succeeds in finding us an open spot in our table. So I see some confused looks. Where is it not clicking? Well, let's do a specific. So we talked about linear probing. This was the idea. If this spot's occupied, let's try the next spot. If that's occupied, try the next spot. And we were using a simple hash function, which was just take the first letter of the key and see where that is in the alphabet, right? So what would that hash function look like? Hash of key probe. So I equals key bracket 0 minus 64. So A gives us a 1, B gives us a 2, Z gives us a 26. That's just ASCII code magic. And now I'm just going to say I equals I plus probe. And I'm going to return I. So what's that going to do? If I hash Carol with probe 0, first character of the string is a C, That's ASCII code 67. Subtract 64, I is equal to 3. Probe is equal to 0, it's going to return a 3. If I were to call this with a probe of 1, again 67 minus 64, I is equal to 3. Going to add a probe of 1, that's 4. I'm going to return a 4. And you can see this is doing exactly what our first attempt at dealing with collisions was doing, which is it just returns successive locations. So that's like sequential probing. But I could do something different. I could do I equals I plus the square of the probe number. So now the first time I hash, I'm going to get a 3. The second time I'm going to get a 4. But the next time, I'm going to get a 3 plus 2 squared is 4. This is going to take me down to location 7. And if I call with a probe of 3, it's going to give me a 3 plus 3 squared. This is going to take me to location 12. So now my successive attempts to store this one key are starting to get spread out. So I'm not as likely to get that clustering. And we're going to want to reduce that modulo 27, because if it turns out to be bigger than 26, we're not going to have space in our array. Returns the index where we're going to try to store the key. Yeah. Oh, that's just the ASCII code. If you look up a table of ASCII codes, the letter C is a 67. So this is just converting it so that an A comes out to a 1, B comes out to 2, C to 3.
So, can we just briefly go over again why clustering is such a bad thing? What are the benefits of?
So the issue with clustering, I may still have a nice picture. The issue with clustering was that, C tried to get stored here. That was in use, so we put it down here. And then Ellen came along and put that in there, and now we tried to do David, and it wanted to go here. If we have another C, right, if we have Charlie, it's going to try to go here, and here, and here, and here, and it's going to have to come down to location 7. And if we had a bunch of names that started with a C, they're all going to go through the same process. They're going to start here, keep going through, and they're just going to stack up linearly. And while they're doing that, they're also taking up the spots where we would normally store a D or an E or an F or a G. Right? And so anytime we have those names, you're going to have collisions. So it just generally works out better if you can distribute these things around. It's a better chance that if you pick a location, it's going to be open, or one nearby will be open. So this is sometimes called quadratic probing. Right, linear probing, we're just adding the probe or some multiple of the probe. Quadratic, we're actually adding the square of the probe. So the more attempts you have, the more space you get between the previous attempt and this one, because squares grow that way. But in general, this hash function can be lots of different things. Right, so we commented that using the first letter of the name is probably not very good. So let's look at a better function. So let's just add the ASCII characters of each letter in the key to a running sum. And then let's add 5 times the square of the probe, we'll subtract 7 times the probe, we'll add 107. Why? I don't know. And then we'll reduce that modulo 1001. And we'll return that. So 2 names that are very close to each other, probably going to give me fairly different results when I go through this hash function. And a good hash function, if you have 2 keys that look pretty close to each other, they differ in like 1 letter, a good hash function should give you different results. There's a fundamental weakness to this hash function. There's at least one fundamental weakness to this hash function. All of those are going to give me exactly the same value, because all I'm doing is adding together the ASCII codes of the letters. And if you have 2 keys with the same set of letters, you're going to get the same hash function. So in here, I might actually take the ASCII code of character I and multiply it by I plus 1. So this would give me the ASCII code of C plus twice A plus 3 times T. This would give me the ASCII code of T plus twice A plus 3 times C. Those are probably going to be different values. So this would be a little bit more of an interesting hash function. We're not going to really deal with what makes one hash function work well. We're not going to delve into the science of designing a hash function based on characteristics of the data. People do that. And it's important and useful, but we're not going to go there. We're going to stick with pretty simple functions like add up the ASCII letters, add the probe, reduce modulo 101 or something. And I'll generally give you a hash function to work with for an assignment or a test question and stuff. So you've heard of MD5 hashes, right? Same idea. So here's the algorithm for an MD5 hash, written in C. 64 integer array S, initialize a bunch of constants which are based on trig functions. Set up these magic constants, and then this works on a 512-bit piece of data, and go through a loop and do all of this crazy stuff and add things together. And basically what you're doing is you're applying these sets of logic operations. So A, B, C, and D are the 4 equal-sized pieces of your 512-bit chunk, and you do these logic operations with some XORs and such, and you apply these in different pieces, and you draw pretty pictures to explain it. And out of the end pops this 512-bit number that's associated with whatever your input was. Sorry, 128-bit number. So here's their example. Quick Brown Fox jumps over the lazy dog, hashes to this. If you add a period at the end, it hashes to that. Right? Very different number. If you have an empty string, it hashes to this. So we wouldn't use this to build a hash table, right? We wouldn't use this as an index into an array because these are huge numbers. But it's still a way to take some arbitrarily long string of characters and associate it with a 128-bit number. And the goal is still the same. You would like to know that if you have different inputs, you get a different number out. That's obviously not always possible because there's only 2 to the 128th possible 128-bit strings. And there's more than 2 to the 128th possible inputs, right? There's a countably infinite number of possible inputs. But realistically speaking, if you were to take all the English sentences that are well-formed sentences and hash them, you'd probably get different results in the end. So we could make a phrase dictionary, and instead of storing, or we could make a book dictionary, right? We could take each book and hash it to a 128-bit number, and there aren't that many books in existence. Certainly nothing close to 2 to the 128. And there's a good chance that if you did this, you could get a unique 128-bit number that corresponds to every book. And if you take this book and you make a typo correction somewhere, you change the to it, right? You'll probably get a different 128-bit number. So this is used for security. When you download a program, you'd see something that says, MD5 hash. And the idea is this is what the hash of this program should be. So download your program, run your own hash calculator, see what the hash of the thing you downloaded is. If it matches what I'm telling you it should be, chances are you got the correct program. They found a lot of vulnerabilities in this, right? So there's ways to defeat this based on the idea that there's gonna be collisions, there's gonna be multiple different things that map to the same MD5. The hope was that you could not find a way to write malicious code and have it hash to exactly the same thing as the original program, but you can. So people use SHA and these other approaches, and those have vulnerabilities too. It's a moving target. So hash functions can be complex and beautiful. We're not going to spend too much time thinking about particular hash functions. So what I want you to take away from this is this idea that our hash function, whatever it does internally, it looks like this. It takes a key, whatever that is, a string of characters, a binary file, whatever we're hashing, and it takes a probe number, which usually starts from 0, and the intent is that this returns an index into our array, and if we put in a different probe number, it should give us a different index. And we'll probe originally with index 0, with probe of 0, and if that gives us a collision, we'll rehash with a 1 and a 2 and so on. So that's how we're going to use these hash functions. All right, questions? So let's look at implementation. Still kind of at a pseudocode level. And I'm really just going to focus on the key array. The data array just kind of comes along for the ride. If we store something at index I in the key, we store the corresponding data at index I in the data array. And when we want to retrieve something, we hash, we look in here to figure out the index where that key is stored. And if it's index 17, we just go to 17 in the data array, there's our data. So I'm not going to really worry about the data piece. It's all what's happening in this key array. And I'm just going to assume a length of 101. And we need to have space in here to actually store the key. So if our key is a string of 15 characters, we got to have space in each of these locations for a string of 15 characters. Okay, we want to store exactly the key that was used inside here. But then we also had this idea of a valid flag. Because again, there's nothing inherent that tells us whether this space is empty or occupied. Because it always looks like it has something in it. So when we store something into this table, we're going to set this valid field to say 1. It's just a flag. So these can start off at 0. All right, so here's where we left off. Suppose we hash Izod with a probe of 0 and we get a location 1. We go into our table, we go to location 1, we check the valid flag. We don't look at the key first, we look at the valid flag. Is there something in this location? Valid flag says no. Go ahead and store Izod there. Set the valid flag to say something's in use. Okay, let's hash Nick, and we get back a 1. Go there, something is in there, right? And we could double check to make sure Nick's not already stored there. But it's not, so we have a collision, so we reprobe Nick with a probe of 1, and let's say that gives us a 3. These are fictitious. It's not any particular hash function that we're working with here. I'm just assuming that when I hash Nick with a next probe of value, it's going to give me back a 3. So I'll go to location 3 in my table, I check to see if it's valid, nothing's in there. So I'm going to store Nick, mark that as valid. Okay, now I hash Lisa with a probe of 0 and I get back a 2. I go to location 2, it's not valid. I'm going to store Lisa there and make that a 1. Can you write code for this much so far? The answer is yes. The answer is absolutely. So what does this look like? Store. Yeah.
So would you have to keep track of the probe that you used, or would you just...
No, we just store it and then we forget how it got there.
We just try different probes?
Yeah, exactly, exactly. So let's look at pseudocode for storing a name. So how do we do this? Set our probe to 0, hash our name with that probe, save that as our index. If we've got a collision, well, no, let's do this barehanded. While our hash table bracket index dot valid is equal to 1. In other words, while we have a collision, increment the probe and rehash. So this is basically saying take the name, hash it into an index. If that entry in our hash table has the valid field set to 1, something's already there. Increase the probe, hash again. Now see, sorry, this is end. Now see if that entry's valid is set. If it is, increase the probe, hash again. See if that entry's valid flag is set. If it's not, we've got a place to store our name. So this location is free. So hash table at that index equals whatever our name is that we're storing. Let's I don't want to say data because data is something else. What should we call this? I'll just call this the name. Okay, so I'm going to say hash table at that index dot name equals name, and hash table at that index dot valid equals 1. And there's your whole store function. It's pseudocode, right? You can't actually write things like this, but you could write it differently. But that's the effect of it, right? So take your name, hash it if you have a collision, hash it again. If you don't have a collision, copy it into this piece of your array, set the valid flag. You're done.
So if I insert another name with same your location number 3, so 1 will be increased to.
So you'll increase that to a 1, you'll rehash the name, hopefully get a location that's free. And that's where you'll put it, and you set the valid flag. Okay, so we can insert into the table. Let's hash Tina, and that gives us a 2. And we go to location 2, we check the valid, we got a collision. So we'll rehash with a probe of 1, and that gives us a 5. And we go to table 5, and valid is 0, that location is available. Copy Tina into location 5, set the valid flag. Okay, now we're going to delete Lisa. So how do we do that? We hash Lisa with a 0, we get a 2, we go to location 2, it's valid, something is in here. Check the name, is it Lisa? Yes. So we're going to delete that. How do we do that? Clear the valid flag. So now if I search for Lisa, I'll hash Lisa, get an index 2, go to index 2, it's not valid. Lisa's not in there. But there's a problem now. So here's the problem. We're searching for Tina. So we hash that name with a probe of 0, we get a 2, we go to location 2, it's got a valid flag of 0. Our first conclusion would be, oh, I guess Tina's not in the table. Because we got a valid flag of 0, this spot is effectively empty. The problem is this wasn't empty a moment ago, this had Lisa in it. And because it had Lisa when we tried to store Tina, we had a collision and we had to reprobe and we came down to location 5. So when we delete this, we need to clear the valid flag, but we need to note that there was something in there. So we need a third field on here. And we're going to call this deleted. And this is originally going to be 0. But when we delete something from the hash, we're going to change that to a 1. So now when we search for something, we do the following. Hash with a probe of 0, go to that location, see if the valid flag is set. If it is, and that's the name, we're done, we found it. If it's valid and it's not the name, we might have had a collision, so we need to reprobe. If it's not valid, but it was deleted, we might have had a collision, so we need to reprobe. If it's not valid and it wasn't deleted, we're done, the name's not in the list. So now if we search for Nick, sorry, let's search for Bob. And let's say Bob returns 2. Sorry, searching for Bob. So we hash Bob with a probe of 0, and that gives us a 2. So we come into location 2, it's not valid, but it was deleted, so there might have been a collision, so we'll reprobe with a probe of 1, and let's say that gives us a 6. Come down to location 6, it's not valid, but it wasn't deleted, we're done, we can say Bob's not in the table. So what does our search look like? So searching for a name. Hash with a name and 0. So we'll call that index. Check entry index in our table. And there's a few possibilities. If valid equals 0 and deleted equals 0, it's not found. Because we hashed to this location, there's no collision, there's no chance that there was ever a collision, because this has never been used, and it's not the name we're looking for, because it's not valid, so table name's not found in the table. So we're done. Okay, if valid equals 1 and the name matches, then it's found. And in this case, the data is in the data array at location index. So we can retrieve the phone number or office location or whatever we were looking for. So if valid is 1 and the name matches, it's found. If valid equals 1 and name doesn't match, what do we have to do? If the name doesn't match, there's a valid name in here. We're looking for Bob. It gave us location 2, and suppose that was valid, but Lisa's not Bob. We got to reprobe, right? So we're going to come down here, which says reprobe. Increase the probe number. Rehash. And go back up here. So we got a few cases left. Valid is 0 and deleted is 0, not found. Valid is 1, either the name matches or it doesn't match. We've got those handled. If valid equals 0 and deleted equals 1, then we've got this case. We're looking for Bob. It comes down here. This entry's not valid, but there was something in there. Could be a collision. Increase the probe, rehash. So same thing. Rehash, go back up to the top. And I think those are our only possibilities. If valid is 0, deleted equals either 0 or 1. If valid is 1, the name either matches or it doesn't match. So there's a good search algorithm. And how do we delete? Well, find where the name that you're deleting is stored in the table. Find the index in the table. That's what all of this does, right? It gives us an index at the end. And then set the valid flag to 0. Set the deleted flag to 1, and you're done. So let's redo the store algorithm in this style. So storing a name. Go ahead and hash it to an integer. Check that entry in the array. So if valid is equal to 0, meaning that entry is not in use, go ahead and store at that location, and you're done. Otherwise, that location must be in use, so increase the probe, rehash. And go back up. So storing is the easiest operation. We're just going to keep probing until we get to a location that's available, and we're going to store it in that location. Doesn't matter if that location previously had something in it or not. If it's available now and we mapped to it with the hash function, we're going to use it. So we don't have to worry about the deleted flag for storing. We only care about valid. Is that cell in use? So we can store, we can search, we can delete. That's pretty much all we need. We need to initialize. How do we initialize? Go through, clear all the valid flags, clear all the deleted flags. And now it's effectively an empty hash table.
So we don't have any null.
No, there's no nulls in here. Make your flags just numbers. And you can make composite flags. You could have one flag field that's 0 if it's valid, and 1 if it's invalid and deleted, and 2 if it's invalid and not deleted, and so on. But it's easy to just use separate flags. So I'm leaning towards having you do a PA3 and hashes, and maybe we'll hash some linked lists or something for fun. But these kinds of ideas. So that's basic overview of pseudocode for hashes. So think about that. Post an ODP Monday morning that will start dealing with some hash functions. No more ODPs for the weekend though, just the one that's open right now. Cool, I will see you next time.